In this video I'm gonna show how to calibrate and run adaptive optical system based on 109 channel piezoelectrical mirror. So let's see what we have in our setup. We have an imaging camera. So what we see here is a live image from the system, from the imaging camera, and we also have a Shack-Hartmann sensor, which we can run the preview by this button. So you see the pattern, and actually the parameters of this Shack-Hartmann sensor can be tuned with MIUI cockpit program. I run it now. I choose the second camera, the FrontSurfer camera, and I try now in this program to set up the optimal parameters like exposure for my visibility of the spots. If the exposure is too high, then actually I cannot use this image for wavefront sensing. So we need to set it to optimal parameter. I believe it's 0.6 millisecond, and to check whether it's really good, we can use this tool, which is called histogram window. If we run it, then it will show the histogram of all intensities in this pattern, and I switch for better visibility to logarithmic view, and we can say that with this exposure all intensity are, so this corresponds to my spots, they actually do not oversaturated. That's a good setting for the intensity. We also can set here the cropping, so like that, and then we can to see these parameters of cropping on size tab. So you see that it's about 460 and 163 from left. We can now close this window and set the same parameters in camera properties in FrontSurfer. To crop it, we make it about 460, and it was about 160 from the left, and the exposure was about 0.6. Yes, this parameter pixel clock actually controls the maximum frame rate which with FrontSurfer can run. If I increase it, then it will be increased as well, but you should never make it too high for your processor unit. So at my computer it runs optimally at 24 megahertz. So let's check now the preview image. I do it like that. Yeah, it's very good. We can crop a little bit from top if needed, but you can work with this as well. So now if I grab the image with this button, FrontSurfer grabs it, and now I need to have right parameters to process the image, and this is done by this option parameters, and then I load the parameters, and I load them from, so that's the file calibration, and you see that in this file the picture source set to file. I need to change it to camera. What's more important, all these parameters like pixel width, pixel height, and distance from the array to the CCD are actually set during the calibration procedure, and you should never change these parameters. Okay, now if we process the pattern, FrontSurfer finds the spots. We see that it has found all the spots, and that's the processed wavefront shape in form of interferogram and also far field intensity. Please notice the similarity of these two images. Very good. Now we can try to calibrate the mirror. For this we need to load proper configuration file. We go here, it's already loaded, but actually you need to load the file that is provided with the system. Okay. You can check whether it works by set values. If I change something here, you see here the image has changed, so I can also press rotate, then mirror sends one by one maximum voltage to every of the channels. You can see that it moves. I'll skip it now because it's 109 channel, pretty long. Close. And now we can try to calibrate the mirror to make. So before we need to check the feedback parameters. This first group of parameters also they are related to calibration of the system. So we set the initial voltage of like that, and that's voltage step. It's so the initial voltage will be set to all of the channels, and then this voltage step will be applied to each of the channels sequentially, and the response functions will be measured. We also set for calibration, we set bigger delay, so the mirror can settle completely between changing channels, and we leave this settings as it is. After that, I press this button, mirror calibrate, and we need to wait. You see that the system sends sequentially maximum step voltage to each of the actuators, and then records the response function. We need to wait a little bit. Okay, all 109 channels were tried. We can check the singular values. We use SVD here. So if the system is properly calibrated, then these singular values, I double click on these red yellow dots. They should be looking similar to Cerny polynomials or some other functions. Here we cut some small values which considered to be noise, that can be considered to be noise. Of course, you can sometimes use all the values and just see what happens, but in this experiment we leave it like that. Okay, so it gives us 88 active modes from 109 channel. Okay, now before starting the feedback, I change again feedback parameters. I change the delay because I don't need such huge delay now. I can make it 1 millisecond or even 0 if you want to run it fast enough, and then we can start the feedback. Okay, you see now that the focal spot changed, so now it's focused. Maybe my imaging camera is a little bit out of focus. I can move the camera, or I can adjust it with the feedback parameters. If I now press arrows button on my keyboard, I can change between the aberration. You see here the number of aberration changed, and up and down changes the value of the aberration. I can focus a little bit more. Okay, so it's about that. So let's try to apply huge defocus. It's some RMS rule. Say -3 microns. Okay, we stop it. We grab the image. Look how the focus is now the far field. We process it, the pattern. It looks very similar, the same grainy structure. So it's not absolutely perfect defocus. What we see here is some print row of actuators. We can run feedback again. To erase the target function, I need to press escape. So it's now again focused. Let's try to obtain some other aberrations like astigmatism, for instance. You see the astigmatism here. Okay, let's make it 2 microns. Stop it. Process it. Yes, again, the 2 spots are very similar. Let's try to create some other aberrations. I reset it again. Another astigmatism. Orthogonal direction. Yeah, let's try to make comma. It's Cernicke polynomial 3.1. Yeah, it's a very good comma. So just comma, let's stop it. Comma of 3 microns. We grab the image, we process it. That's the comma, and you see the image. It's very similar. We can also check the report. In a report, you see that now it's our aberration 3.1 comma is generated, and the value of this in waves is 4.7, which is approximately 3 microns. Okay, with this mirror you can actually generate aberrations of higher order, not only comma or trefoil. That's trefoil. Okay, let's make it again 3 microns. Stop. Grab. Process. That's the trefoil we see. A little bit with some mistakes. To decrease this mistake, you need to have lower amplitude, because 3 microns is really on limits of the mirror. Let's make other aberrations, like spherical aberration. In this direction it saturates, because the mirror has some initial shape, has some preferences, but in this direction I can go up to -2, -3 micron. Still RMS is not very high. I can stop it. Oh yes, that's spherical aberration, and exactly what we see here. Some edge effects, because my pattern was not very good centered here, and I lost some spots. That's why we see here some edge effects. Mirror star feedback. Let's generate 4.2. Yes. Check further. 4.4. say 2 microns. Yes. Start feedback. I move again here with my cursor. 5-1. It's a comma, higher order comma. So very similar. Start feedback again. Let's check higher order. Spherical of 6th order. 6-0. You see, the RMS is already about 0.1 waves, which is pretty high, even for half a micron. Maybe in other direction it will be better. Yes, it is. So we can make minus 1.5, and let's check whether we've got the same in far field. Yes, it's a spherical of 6th order. Sombrero hat. Okay, so that's it. It's pretty simple. You choose the aberration, you set its amplitude, like 7.1. You check that the RMS is still, say, below than 0.1. You stop it, grab the image, and process it, and you can verify. Oh, very nice picture. Okay, that was it.